The Coulomb force between a point and a line. Recall that Coulomb's law states that if we have two charges, Q1 and Q2, separated by a distance r, then the electrical force between them is kQ1 Q2 over r squared. Here we'll use Coulomb's law to find the force between a point charge and an electrically charged line. So suppose we have a point charge with charge Q. Q could be positive, negative, or 0 if the point charge is neutral. And let's say we have a line of length 2L. Let's rewrite the length as L plus L, since in this problem we'll assume that the point charge Q lies along the midline of the line. And let's also assume that the line has a uniform linear charge density, that is, a charge per unit length, of lambda. Like Q, lambda could also be positive, negative, or 0. And finally, let's say that the distance between the point charge and the midpoint of the line has length z. So given this setup, what's the Coulomb force between the point and the line? Well, it's 2kq lambda L over z root L squared plus z squared. We'll be proving this here. The sign of this result also indicates whether the force is repulsive, as we've drawn it here, or attractive. Now what happens if the line is infinitely long? Well, if the line still has a charge density of lambda, then the force is now 2kq lambda over z. We'll be proving this result as well. Now let's return to our original setup with a line of length 2L. We're going to take advantage of the symmetry in this problem. Consider a segment of the line over here. It will exert a force on the point charge in this direction. If we consider a similar segment on the opposite side, it exerts a force that's reflected across the y-axis. Adding these two vectors together, we see that their horizontal components cancel and we're left with a purely vertical force. No matter which place on the line we look, the opposite side of the line will produce a force that cancels the horizontal component. So by the symmetry of this problem, we know that the final force has to be vertical. So as we proceed, we'll only consider the vertical components of forces. So here's the game plan. We're going to consider a small segment of the line like the one shown here. Each little segment results in a force on the charge, and we want to find this force's vertical component. And then we integrate these vertical components over the entire length of the line. So that's the plan. Now let's look at a specific segment of the line. And we'll say it has length dx. So this segment has charge lambda dx, since lambda is the charge per unit length of the line. So we'll hold on to that for later. We're defining x here as the distance to the right of the line's midpoint. So all the way on the left end, x equals negative L, and all the way on the right end, x is positive L. But for now, we'll suppose that our segment is at position x. We want the force dF between dx and q. More precisely, we want the vertical component of this force. So if we label this angle here as theta, then the vertical component is dF cosine theta. But how can we find the cosine of theta? Well, let's draw on the line connecting q and dx, and notice that we have a right triangle here shown in blue. So by the Pythagorean theorem, the hypotenuse of this right triangle is root x squared plus z squared. We can draw on the angle theta in this triangle as well, and so we see that the cosine of theta is the adjacent over the hypotenuse, or z over root x squared plus z squared. Now let's also remember that we can find an expression for dF using Coulomb's law. Coulomb's law says that dF will be k times q1 times q2 over r squared. What are our charges q1 and q2? dF is the force between the point charge q and the segment dx, which has charge lambda dx. And r, the distance between these charges, is root x squared plus z squared. So let's clear everything out for a second. We want to define an expression for the vertical component of the force, that is, dF cosine theta. So here's our expression for dF using Coulomb's law, and here's our expression for cosine theta using some trigonometry. At this point, we can simplify our expression a little. Squaring the square root just gives us what's under the root. Let's move the dx to the outside, and let's combine the denominators into a single expression. X squared plus z squared times root x squared plus z squared is x squared plus z squared to the 3/2 power. So we'll hold on to this expression. Remember, we wanted to integrate the vertical component of the force over the entire length of the line. So the total force, F, is the integral of dF cosine theta, the vertical component. What are the limits of this integration? Well, the limits of the line are x equals minus L and x equals plus L. So those are our limits. Let's clear this out and sub in our expression for df cosine theta. At this point we're done with the physics and it's purely a math problem now. We have an integral that's over the variable x. K, q, lambda, and z don't depend on x, so we can pull them out of the integral. So what is this integral? I'll just tell you that the integral of 1 over x squared plus z squared to the 3 halves with respect to x is x over z squared root x squared plus z squared. And the limits of this integral we said are plus and minus L. So evaluating this expression at x equals plus L gives this expression. We just plugged in L wherever we saw x. And we subtract our expression for minus L. Minus L squared is just L squared. And also the minus sign in front of the L cancels out the minus sign in front of the second term. At this point, notice that these two terms are identical, so we can combine them. And put a 2 in the numerator. So we've evaluated the integral, and we can move it back to our expression for f. We have a z in the numerator and a z squared in the denominator, so we'll have some cancellation, and we can move things around for our final expression. So here's our result for the force between a point charge and a line. But let's look at this a little more. We drew the force as repulsive, meaning it's positive. This is the case when q and lambda are both positive, and our result predicts this. When q and lambda are positive, f will be positive. The same goes for when q and lambda are both negative. When one is positive and the other is negative, f will be negative, meaning it's attractive. So our result is correct for all q and lambda, whether they're positive, negative, or 0. Now what happens when the line is infinitely long? Well, that's equivalent to saying that L is much, much greater than z. So in the root L squared plus z squared, we can neglect the z squared term. And now we have L in the numerator and root L squared, which is just L, in the denominator. So those will cancel out. And here's our final result for the force between a point charge and an infinite line. Something neat to note about this is that Coulomb's law is an inverse square law, but when one of our charges is a uniformly charged infinite line, the force between that line and a point charge, a distance z from the line, varies with 1 over z rather than 1 over z squared. Okay, one more thing. Let's check our units. We know that Coulomb's law says a force should be k times a charge times another charge, making that charge squared in the numerator, over a distance squared. So q is a charge, and z is a distance in the denominator, and lambda is a charge density, or charge per unit distance. So combining these units gives us charge squared over distance squared. Multiply that by k, and 2 is a constant that doesn't have any units, and sure enough this gives us a force, so the units check out.